theorems. Okay, so we've been looking at similarity and proportion theorems. We've had a look at how to use them sort of individually, but as I keep saying to you guys, the way this is tested is them together. So we need to be able to prove similarity in order to get proportions like we have here, and then in order to get different expressions that we've manipulated from a proportional triangle, triangles that are in proportion. So over here, we prove similarity, and then in question A, we had to get the ratios equal. So remember, once you've proven similarity, you put first two sides over first two sides, second two over second two, third, first and third, first and third. And then you can decide which fractions you want to work with, and you can prove the ratio. Just for question B, what I want to point out here is the fact that you've got an AB squared. So basically what you're looking for when you go back to your original ratios that you got from the similar triangles, you want to look for two ratios that each contain an AB. So this is why I went with the first two, because you can see that there's an AB in the numerator of the first fraction and AB in the denominator of the second fraction. When you go and cross multiply, AB times AB gives you that AB squared. So always just look out for those things. That I kind of say this in trig, but it goes with maths in general. You almost need to be 2 steps ahead of yourself. You need to think, okay, well, how do I get something that's squared? I have to have 2 of those things. So I'm looking for an AB and an AB, 2 ABs. So it's a skill that comes with practice, hence the boot camps, hence you need to go through past papers. So it does come with practice, but you do almost need to be 2 steps ahead of yourself when you're doing specifically geometry and trig, because it's just going to sort of guide you to where you need to be. Alrighty, but that was from last lesson. Clearly this public holiday is just messing with my time sensing abilities. So that was on Monday. Where we're at today is having a look at some past paper questions, just that we can get an idea of how is this actually going to be asked in exam. Now, I just want to remind you guys, similarity and proportion is not a huge part of the geometry in your paper. The bulk of or majority of the geometry is actually circle geometry. And you'll see when we go through these past papers that often what's going to happen is we'll give you a circle geometry question. And then the last question or two will then involve similarity or proportion. It's not a lot of marks in your exam. So geometry, it's probably 35 to 40 marks in your exam. It's a huge chunk. And then the similarity and proportion of it is maybe 8 to 10 marks. So it really is not a lot of the geometry. So that's why I'm saying don't stress too much about it. If it really is not your thing, that's okay. But we can do well in it if we practice it and if we apply the things that we've spoken about already. Okay, but let's get into this first question. Now, this first question is a little older. I'm fully aware of that fact. But it's a nice question because it goes back to quads. Now, the last time you guys really did quads is in grade 10, where you actually probably did quadrilaterals as part of your content. And so it's really important that you do remember your properties of your quads, because even though it's not necessarily a case of we're specifically going to test you on quadrilaterals, quadrilaterals will come up in analytical geometry. And quadrilaterals can come up in Euclidean geometry. So if you think about things like cyclic quads, that is a quadrilateral. Obviously, we're using circle theorems, but quadrilaterals do come up, and it's just something that we do in grade 10, but that we don't really deal with it ever again. So this is a nice question just to refresh our memories of some properties of quadrilaterals that we need to know. Alrighty, so let's make this a touch bigger so we can see what's happening. In this question, we have been told that ABCD is a parallelogram. Sorry, I'm gonna get on it. So we've been told that ABCD is a parallelogram. Now, ABCD is the big quadrilateral that we have here. I'm obviously not doing it in order, but that doesn't matter. We're just gonna roll with it. And the second, so guys, remember, the second I tell you it is a parallelogram, or it is a rectangle, you can automatically assume that all properties of that shape apply here. So we automatically know, yes, it's given to us on the diagram, but we automatically know both pairs of opposite sides are parallel. We automatically know both pairs of opposite sides are equal. We automatically know that the diagonals bisect each other, etc., etc., etc. So because I've told you what it is, you can assume all of the properties are true. We're then told that the diagonals of this parallelogram ABCD intersect at M, which is this point over here in the middle with the yellow dot. F is a point on AD, so here's F at the top here, such that AF to FD is 4:3. Now remember though, English, these are not lengths that we're given. This is a ratio that I'm giving you. So it's just telling you what proportion these sides are in. So AF is 4 parts. I'm just going to use X, whereas FD is 3 parts. That obviously means that we know that the whole length AD is 7 parts. E, so E is, we can see E sort of in the middle on the diagonal, is a point on AM such that EF is parallel to BD. That's the one with 3 arrows on it. I'm going to highlight all the parallel sides in a second. And MD, FC and MD intersect at G. We have all of that. Right, just quickly with the parallel lines, because there are quite a few of them. We have obviously got the opposite sides of our parallelogram parallel to each other, so AD and BC. We then also have AB and CD. And then we were told with that point on E, excuse me, that point on E, EF is parallel to the diagonal BD. So we've got quite a few pairs of parallel lines, and we did chat about the fact that the second that there's a lot of parallel lines, it does get a bit confusing. We need to be careful. All right, but let's get into the question. So the first question is asking us to calculate with reasons the ratio of EM over AM. So the first thing that we obviously want to do is figure out, well, where the heck are those sides or those segments? So EM is the side or segment over here. AM is then the entire sort of bisected diagonal portion. All right, that's fine. A little tricky because I know nothing about those two segments, but what I want you to have a look at is the fact that, there's so many colors we've got going on here, is the fact that in triangle EDM, so this pink triangle I have going on here, we know that EF is parallel to MD that was given to us. And because we've got one side or one side of our triangle parallel to a line, we know that the proportion theorem applies here. So remember, proportion theorem states that when a line is drawn parallel to one side of my triangle, it cuts the other two sides in proportion. So we know that EF is that parallel line drawn. It's parallel to one side of my triangle, MD or DM, whatever you want. And so it's cutting my sides in proportion. That's great, because if you have a look, we have a proportion for AF and FD, which means we can now use that to work out what the ratio of EM over AM is. So we're going to now set up our ratio. We know that EM over AM is equal to, now remember you match it up, so EM matches up with FD, and AM is the whole side length, so the whole side length AM matches up with AD. And this is because of prop theorem. Obviously, remember, you can also use line parallel to one side of triangle as your reason. If you use prop theorem, you have to state your parallel line, so EF parallel to DM. Because there's so many parallel lines in this diagram, we do need to make sure we state them. And then because we know that FD over AD has already got a ratio, we can now state that EM over AM is equal to. Now the ratio of FD was 3x, so 3 parts. And remember I said earlier, because we were given AF and FD, we automatically know what AD is, 7 parts. So that ratio is 3 is to 7. And so now we're starting to gain more information about what's happening in my triangle here. All right, guys, just remember, any questions, please do ask. I'm going to move on, but you just ask if you've got questions. We've then also been asked to give the ratio of EM CM over ME. So again, let's go find where those sides are. CM is 1/2 of the diagonal, and ME is the other segment of my diagonal there. Okay, cool, no problem. This is now where your knowledge of quadrilaterals comes in. So can anyone tell me, and you can put it in the chat so you can unmute yourself. Can anyone tell me, and I did already mention it, so let's see who is listening, what the relationship or what happens with your diagonals when they cut each other? What is the relationship with your diagonals in a parallelogram? Because remember, this is a parallelogram. Good, Wami, they bisect, awesome. So that M, that point M is cutting my diagonals in half. Now remember, what we have just shown is that this AM over here is 7 parts. It's a weird looking situation that we have going on here. So let's try that again. So we just proved in the last question that all the way from A to M, we've got 7 parts. Oops, whatever. Because that's the case, and because, as Wami said, the diagonals bisect each other, this is also 7 parts. It's not 7 centimeters, it's not 7 millimeters, kilometers, whatever, it's just a ratio. And because of that, we can now go and find the ratio of CM to ME. We've already shown that ME, if you have a look in your first question, was 3 parts. 3 parts, okay, that's a weird looking 3, we're just gonna roll with it. And we now know that MC is 7 parts. So we can use that information. And this is, again, where those properties of your quads is important. We can't just obviously go and say that. We need to give some reasoning for all of this. And the first thing I can state is that I know that AM is equal to MC because of diagonals of a parallelogram. And parallelogram, you can just write as palm. Right, remember mathematicians are quite lazy, especially in geometry. Our reasons are abbreviated: diagonals, diag, and palm is parallelogram. So because we know that, and because we've already proven that AM is 7 parts, we know that CM over ME is equal to 7 parts over the 3 parts of ME. And that's it. So very easy question if you remembered your properties of quadrilaterals, and specifically of a parallelogram. Okay, 9.2.3 is one that I would classify as a complex question in this section. It's understanding or bringing in knowledge from a few different sections, but also just understanding what you're seeing on the diagram. So here, 9.2.3, we've asked for the ratio of the area of triangle FDC to the triangle or area of triangle BDC. So FDC is this long skinny triangle on the side here, and BDC, let's go purple, is this big triangle over here. I'm fully aware that there are a lot of colors going on. I do understand this. We just need to be able to see exactly what we want. Okay, so my first question, guys, how do you work out the area of a triangle? You're welcome to unmute yourself, or you can just put in the chat. What is the formula, or how do we work out the area of a triangle? There's technically 2 ways to do it, but give me one. Nice. Owami's on it. Does anyone know another way? So Owami said half base times height, which is awesome. That is the one we're going to use. But how else could you work out the area of a triangle? Let's see who remembers. Nice. Okay, the area rule from trig. Now, sometimes you use the area rule. Sometimes you use half base times height. It's very much going to be dependent on obviously what you're given. Remember, area rule is half AB times sine C, which is basically two adjacent sides and the angle in between them. So that is part of your 2D, 3D trig. You can go and obviously have a look at past papers if you need to refresh your memory. But there's two ways to work out the area of a triangle. We're going to stick here with half base times height, and I'll tell you why that is in a second. But just remember half base times height. It's one of those formulas that we just expect you to know. Cool. So if we look at the two beautiful triangles that I've highlighted, I don't know how to phrase this question. What is the same in both of these triangles? So think about the half, the base, and the height. What is the same in both of these triangles? Have a look at them. Obviously, half is constant, but what is the same in both of them?
Is it maybe that they both share the side DC?
They both
Share the side DC.
Okay, I like what you're thinking. So we could have that they both have the same base DC. Not upset about that. But if we, and specifically when we start looking at proportion and similarity, so I like where you're thinking of what do they have in common. When we start looking at triangles and specifically areas of triangles, what we want to try and have a look for is triangles that fall between the same parallel lines, because remember, parallel lines, if I could draw a parallel line, are not only parallel to each other, so not only have the same gradient, that's pretty defining of parallel line, but the distance between them at any point is always the same. So they are equidistant from each other. Sorry, they're equidistant from each other. And because both the triangles here fall between the parallel lines AD and BC, it means that their perpendicular height is exactly the same. So they both have the same perpendicular height. So what that means is when I go and substitute into my formula, and I was not going to look a bit gross because I've got so many halves, but I've got half base times height divided by half base times height. Because those heights are the same, they are going to divide away, and so are the halves. And so all you're actually left with is a ratio of base to base. So base length to base length. If we then consider what the base lengths would be in these triangles, so look at the beautiful perpendicular height thing I've drawn. The base length in the green triangle would be FD. So it's FD over, and the base length of my purple triangle would be BC. Okay, now, again, what I want you to remember is that we're trying to use side lengths we know information about. FD, I know that was 3 parts. BC, I've got no information about, but remember we were told this is a parallelogram. Opposite sides of a parallelogram are equal, which means that if AD is 7x, BD is the same thing. So we actually have all of the information that we need. So whilst you might be thinking, okay, cool, well, the heights are the same, but that's the same thing if the bases are the same. Absolutely. But bear in mind, if your bases were both DC, your perpendicular height is a little harder to work with. So you would need to go and then figure out each of your perpendicular heights for these triangles and ensuring that you still know what those lengths are in terms of a ratio. Here, because I knew what FD was and I could very easily work out what BC was, I basically knew what it was. I was going to work with the same heights. So FD, as I said, was 3 parts. We're not even going to use the X, so it's parts. And BC is 7 parts. Now, what I want you to remember is that there's a reason for it. We can't just make the statement. We know that BC is equal to AD because opposite sides of a parallelogram are equal. So much in the same way as we had to say earlier, the diagonals of a palm bisect each other, we do need to make the statement that opposite sides of a parallelogram are equal. But once we have that information, we've got all that we need to work out the ratio of the areas. And so in this case, the ratio of my areas was 3:7. So one of the things to look out for when they do ask for areas of triangle when it comes to similarity and proportion is that same height situation. Do the triangles fall between the same pair of parallel lines in order to give it the same height? Alrighty. So these are just working out some ratios using similarity and proportion. A slightly more complex question of the area of triangles, but like I said, look out for the triangles falling between the same two parallel lines, and then you're able to simplify it so much easier to just work with the area of bases. Right, so let's take a screenshot and then we'll have a look, obviously, at another example that will now involve circles. So we're going to have to involve some circle theorems, but still similarity and proportion. And remember, guys, if you have questions, please ask. Okay. Right, so if we look at example 2, there's a lot going on here, and I think this is also sometimes a moment where we're like, no, like my shirt says, nie vandag nie. Just no. I don't want to deal with that, but we have to deal with it. And the important thing here is that we read our information carefully and that we go step by step. Don't try and take everything in and try and do everything at once. We're going to go step by step. In the diagram, PK is a tangent to the circle. Great. The second we see tangent, remember I said this last week, think of tan chord theorem and think of tan perp rad. If we don't know where the center is, obviously tan perp rad falls out the window, but tan chord, absolutely. So we know we've got a tangent here. And that is PK. So this thing I'm highlighting in yellow here. Chord LS is produced to P. I'm not going to leave this highlighted, but just so we can see. So here's chord LS, and it's then extended all the way to P. That's what produced means. It just means extended. N and M are points on K and P, are points on KP and SP respectively, such that MN is parallel to SK. So here's MN. Not a great highlighting ability I have. And obviously SK over here as well. Okay. It was really bad all around, so we'll just make another attempt here. MN SK. All right, so we've got some parallel lines. And immediately you see parallel lines, and you start thinking, okay, prop theorem. Where are my triangles at? What am I going to use? Then it says chord KS and LN intersect at T. We can see point T there. We can see where those chords intersect. Great. We haven't been given the sizes of anything, so we don't know side lengths or angle sizes or anything, but that is what we have. The first question says, prove with reasons that angle K4 is equal to NML. So here's K4. K4. And NML is this angle over here. So basically M2 and 3. So I want you to take a second and I want you to think about how we can prove that K4 is equal to NML. So the two angles I've indicated there in red. And remember, every bit of information we've given you is useful. We don't give you useless information. So the tangent information, useful. The parallel line information, useful. Okay, I've got a suggestion of tan chord. I agree. Can you tell me which angles would then apply in this tan chord application? So which angles are we talking about in tan chord? Okay, Leila, I will go back to the first question when we're done here. So as soon as we're done with this question, I will go back for you to take a screenshot. All right, so cool. So we have got the tangent PK, which is highlighted in yellow. And here's our chord KL. I don't know what's happening. KL, whatever. Okay. Because of that, we know that angle K4 is equal to angle S1 because of tan chord theorem. So K4 is equal to angle S1 tan chord theorem. So that is exactly, I think it was Kanisile who mentioned tan chord theorem. I wish this thing would highlight so that we could actually see what we're doing. Okay, so here we go. And because of the angle created here at K4, that's then equal to S1. There's your tan chord theorem. Now, the next bit that's really useful to us is those parallel lines. If you have a look, we've got that F shape. We've got corresponding angles, which means that this whole angle NML corresponds to angle S1. So NML is equal to angle S1. I'm fully aware of the fact that this pen is quite thick, but we're rolling with it. Corresponding angles, because MN was parallel to S. Okay. Now, guys, what you should notice, to remember, if we go back to what we're trying to prove, we're trying to prove that K4 is equal to NML. That's, I want to say our burden of proof, but that sounds weird. We've got K4, we've got NML, and what we see is that both of them are equal to S1. If they both equal S1, then they have to be equal to each other. So therefore, angle K4 is equal to angle NML. And if you want to, you can put as your reason both equal angle S1, because that is why they're there. There were so many that's that didn't need to be there. That is why they are equal. Because they both are equal to S1, they both have to be equal to each other. It's sort of if y equals x, no. If x equals 2 and y equals 2, then x and y are the same thing. So once we've proven that they're both equal to S1, we have shown that they're equal to each other. And again, so it goes back to there are no useless bits of information that we give you. The tangent was important and the parallel lines was important. And so we need to be looking at those bits of information. Right, I'm going to leave the red on just so we can see which angles we now know are equal to each other, because it might be useful later on. And 11.2 question B says, prove that KLMN is a cyclic quad. Okay, now remember, a cyclic quad means that all four vertices touch or lie on the circumference. So KLMN is, okay, we'll get it eventually. Here in blue. It's not my best highlighting sort of showcase that I've ever done in the world, but I can't very rarely get anything right here. Okay, so it's that blue quadrilateral. We can very clearly see that it is not on the circle, so we can't automatically say it's cyclic. We have to prove it. Now, there are three ways to prove a cyclic quad. Either you need to show that the exterior angle is equal to the opposite interior angle, Or you need to show that the two of your opposite interior angles add up to 180, so are supplementary. Or 3, you need to show that angles in the same seg are equal. Now remember I said I've left the red angles on there to show us what we already know are equal. So I want you to take a look. And I want you to think about, do we already know 2 angles that are equal to each other that allows me to state that KLMN is a cyclic quad? So take a second, have a look. Let me know what you think. So look at the red angles, see which ones are equal. Do they help us prove this is cyclic? No one grade 12s, okay. Just because I don't want to sit in silence for the last 20 minutes. I've just put in the block, a reminder. Oh, no, can you see it?
Ma'am, I was gonna say that is the exterior angle, the one that we proved before, where we said K4 is equal to S1. We could use that to prove it.
Nice, exactly, amazing. Okay, so exactly what Kanyisile said there. I will write it down formally in a second. So I put the 3 weights down there, and Kanyisile has used the exterior angle one. If you go and have a look here, K4 is the exterior angle to this quad. We can see it very clearly is the exterior angle. And if you then move to the opposite interior angle, we've already proven that NML is the same thing. We've already proven that K4 is equal to angle NML. And so we've already proven that this is a cyclic quad. So we can now go say, cool, I have already proven in the first question, question A, that K4 is equal to angle NML. And because you have proven it, guys, you can just say proven. It's not given, it's proven. You have to go and prove it. And so therefore, KLMN is a cyclic quad. And our reason, you can phrase this reason in a couple different ways. I just say converse exterior angle of cyclic quad. You can phrase it and say exterior angle is equal to opposite interior angle. That's absolutely fine. I just use converse. So there's 3 cyclic quad proofs, or 3 cyclic quad theorems. The converse of all of them prove that it is a cyclic quad. So hence why I use converse. It's really fine however you choose to phrase it. So either you're saying exterior angle is equal to opposite interior angle, or exterior angle, cyclic, converse exterior angle, cyclic quad. Just remember, while I'm on this whole reason thing, I did upload on Google Classroom a list of acceptable geometric reasons that you can use. Alrighty, so just quickly, if you didn't get a screenshot of the first question, here it is. Just make it a touch smaller. So there's question or example 1. Quickly take a screenshot, and then I'm going to move down to the next question, this one. And you're going to try this next one by yourselves. It's proving similarity. Get there now? Cool. So this next question, 11.2.2, says prove that triangle LKN is similar to KSM. Okay, now there's a fair amount of highlighting we have here. So I'm just going to take off the cyclic quad stuff. I'm going to leave the red because obviously we know it's proving similarity, angles is important. And so we have been asked to prove that triangle LKN, which is the purple triangle up here. Obviously, I can't draw a straight line for anything today. Okay, so let's try again. Okay, so the purple triangle is similar to KSM, which let's do in blue. KSM is this blue triangle over here. Okay, now what I want you to bear in mind is that you have just proven that KLMN is a cyclic quad. And because you've just proven it, you can use that fact moving forward. Okay, what I'm going to do is I'm going to do this, and I'll just quickly put little dots on this diagram of the angles we already know are equal. So we know K4 is equal to S1, which is equal to that whole angle. You can also ignore me now. I want you to try this. So ignore me talking to myself. So you're proving similarity. Remember, because you've got no information about any of your side lengths, you're probably going to have to use angle, angle, angle. Okay, so that is all the information that you know. And you know, I'll just go over it, that KL, you know the cyclic quad. I'm going to give you like 2 or 3 minutes, probably 3 or 4 minutes actually. Let's try and prove that that's similar. And the diagram on the right is all the information that you know. Okay, guys, I'm going to give you 1 more minute and then we'll have a look. Remember, similarity, because you've got no information about your sides, you're going to have to use angle, angle, angle. So you're looking for angles that correspond with each other. Okay, let's have a look. All right, so purple and blue triangles, and we already know the red angles are all equal to each other. So that's information that we know. Because of that, we're just going to have to be mindful about which angles we are saying are equal and make sure that we are actually working with the corresponding angles. The first one that I noticed straight off the bat, though, because I've proven the cyclic quad earlier, is the fact that M3 is equal to N3, because what you can see is the bow tie shape, and those are then angles in the same seg in that cyclic quad I've already proven. So N3 is equal to M3, yeah, sorry, just want to make sure my numbers are right. And this is because of angles in the same seg. Right, so that's the first thing that I notice. Oh my gracious. Now we just need to be mindful of where we're working from there. So the next thing, hopefully, that we can see, also because of angles in the same seg, is that, and we're going to have to go a bit roundabout here, but it's fine. L1 and M2 are equal to each other. Now you might be thinking, why on earth is that even important to me? Especially because M2 isn't even in one of my triangles. It's not even an angle that features anywhere. But what you need to remember is that you had those parallel lines. And because of the parallel lines, you've got alternate angles here. And so M2 is equal to K2. And now that is an angle in one of your triangles that corresponds with angle L1 in the purple triangle. So we almost had to do a bit of roundabout work there. In order for us to get that what is that now? K2 was equal to L1. I had to first go and show that L1 was equal to M2 and then use alternate angles. So just remember, guys, you don't always get there straight away. Sometimes you've got to do a bit of work before you get there. And remember, again, no piece of information we give you is useless. Those parallel lines were there for a reason. You proved a cyclic quad for a reason. So the first thing we said that was L1 was equal to M2, because again, angles in same seg. And once we had that, we said that M2 was equal to K2 because of alt angles. Alt angles, there we go. NM or MN doesn't really matter, parallel to KS. And because of all of that, because both L1 and K2 are equal to M2, they are equal to each other. It's the same conversation we had earlier. Okay, so now you've got those pink angles there, L1 and K2 equal to each other. And remember, the second you've got 2 of your 3 angles, you know the third is automatically equal. Oh, so the third in this case is, and just be careful you are labeling your angles correctly, NKL, so let's just get another color here. This whole angle up here is then equal to angle S2. Those are the third angles in my triangles that I'm working with. So NKL is equal to angle S2. And remember, it's just some angles in triangle. So really, grade 12s, and again, we've said this before, the work comes in and you just trying to prove two of your angles are equal. Once you've got two, you've got three. So now we can say, therefore, apparently we can't. We can now make the statement that they're similar. So therefore, triangle LKN, double check your order. We 99% of the time give it to you in order, but just check. Angle L matched up with angle, just make sure we got this right, K. Angle K matched up with angle S, and angle N matched up with angle M. They are similar because of angle, angle, angle. Right now, guys, I can't speak English today. It's just gone down the toilet. Now that you have got the fact that the triangles are similar, we can go a step further and start to work out side lengths. Okay, so in the next question, it says, if LK, so LK is this here at the top, is 12 units, and 3KN equals 4SM. Now remember, this is a ratio, we can manipulate this. If we divide I don't know how to say this in better words. If we put a ratio, so if we say KN over SM, so basically divide both sides by SM, and we get rid of the 3 by dividing both sides by 3, we get a ratio of KN to SM is 4:3. So KN is 4 parts, SM is 3 parts. We want to determine the length of KS, and KS is this length over here, the purple highlighted length, right? And this is now where the fact that we've already proven the triangles are similar is important. If you have a look at all of those lengths I've given you, LK, the 12 units, is a side length in the similar triangles. The 4 parts, KN, is part of your triangle. SM, part of the similar triangle. So we are going to use the fact that they're similar to go and prove. Now, this is where, remember, we set up our ratio using the first 2, the second 2, and the first and third. So LK over KS is equal to KN over SM is equal to LN over KM. And then we pick the sides that are going to work for us. Pick what you already know. We are obviously looking for KS, so automatically I need to choose the ratio with KS. I was given LK, and I was given a ratio for KN to SM. So I'm going to use those first 2 ratios there. And then you just substitute in what you know and you go and solve for it. So we are looking for KS. We know LK is 12 units. Is equal to, now remember the ratio of KN to SM is 4/3. We're not a huge fan of the fact that that KS is in the denominator, but remember any fraction or any ratio you can just flip. So we can flip this to be KS over 12, and we just flip the other side as well, 3/4, which means KS is equal to 3/4 times 12, which means that KS is 9 units. So remember again, we're asking you to do stuff that has relevance. I'm asking you to prove similarity because it's going to be useful for you. I'm not asking you to do it just to make you do it and not enjoy the question. All right, so this is going to be a very small screenshot. I do apologize for this. Let's see how much we can get. Oh. Okay, there we go. All right, so just remember, once you've proven similarity, you can go work out any unknown lengths that you need. We will give you information, obviously, to do that, because before we got there, we had no information about any of our sides. And what I did in terms of writing my information on my diagram, that's really useful because you can start to see where the side lengths or where the ratios are and whether or not it fits with the similarity or the triangles you have just proven to be similar. All right, guys. But there it is.